All right, howdy folks. Let's look at chapter 2, section 8. This is about derivative as a function. This is going to be a bit theoretical, okay? There are problems, but there are not as many problems. It's a wonderful section, and for all the higher level stuff that you would be doing, you really need this stuff. Okay, what is derivative as a function? So earlier we looked at what in the world is the derivative of a function f at a point a, right? At a single point a, x equal to a. What's the derivative of a function? It's the slope of the tangent drawn to the curve at that point. You agree? There's a function, and you want to find the derivative at a point, so you draw a tangent to that curve at that point, and whatever is the slope of that tangent, that's the derivative of that function. That's one way to understand it. And another way we saw was using this limit definition. That is, f prime of a is limit of the quantity f of a plus h minus f of a over h as h approaches 0. Right? Now, can we extend this concept, like go from a single point, derivative at a single point, to derivative as a function itself? What in the world would that mean? Well, so far as this definition is concerned, all we need to do is change that a into an x. So earlier we had f prime of a, now we have f prime of x. And earlier we had f of a plus h, now we have f of x plus h. Similarly, f of a, we have f of x now. Is that all the difference? Yes and no. So far as the formula is concerned, yes. But there is a tremendous amount of significance to this one. In the sense the difference is, x is now a variable. A is a constant at one single x value, but now we are saying that we can extend this and write f prime as a function. Okay? If you didn't quite get it, that's okay. I'm going to show you quite a few examples. And so here, notice what I am saying. One way to find this derivative function f prime of x is to draw a tangent at every point on the curve of y equals f of x and record the slope of that tangent. This is what I'm going to show you with the help of Geogebra. Okay? Give me just a second. Let me go over there and open up my Geogebra. Yeah. So, let's see. What do we notice here? I don't want to be showing this guy. Okay, here is the situation. This red thing that you see, that's the graph of some function y equals f of x. What function is that, man? Don't worry about it. Okay, some function y equals f of x. And now, can we find this function called f prime of x? F prime of x is just like f of x, sort of like f of x, you know. It's another function. And to find that, what did I say we need to do? We need to record the slope of the tangent at every point on this curve. Right? So, let's get busy. Now, at x equals the leftmost point, whatever it is, I drew a tangent to the curve. Right? How do you draw a tangent? I already told you how to draw a tangent. You pick, that's the limit of the secant lines. Right? So let's assume that we went through all that process and we drew a tangent. Now, what's the slope of the tangent? the slope of the tangent, it turns out to be some number like 11.75. So when x is negative 2.5, at least in my case, the slope of the tangent at that same x, negative 2.5, is 11.75. So what did I do? I recorded that value as a point, same x value of negative 2.5, but the y value is this 11.75, whatever the slope of the tangent is. Cool? And now I'll come back to this thing and move it slightly to the right. And when I moved slightly to the right and picked another point on the curve of y equals f of x, another way of looking at it is at a different x value, an x value of negative 2.49, when I drew the tangent, the slope of the tangent turned out to be 11.62, right? So I plotted that. So there is another point, and I keep doing this. I keep changing the point at which I'm drawing the tangent, and each time I'm figuring out the slope of the tangent. And drawing with those y values, which would be the slopes, I'm drawing a whole bunch of points, which is what you are seeing. This A is nothing but a different x values what the slope of the tangent is, right? And I keep doing this, and notice what happens. I sort of get a curve. Isn't that fascinating? What is that curve? That is the derivative curve. That is the f prime of x curve. That's the point, folks. So look at that. All I'm doing is at different points, I'm drawing the slopes, I'm drawing the tangents and recording the slopes of those tangents. Ta-da! So the parabola looking curve, the parabola turns out to be the derivative curve. And in fact, I actually know how to take the derivative in a slightly different way, and I did that. And it ended up that, where's my curve? Yeah, g of x equals f prime of x, right? That's exactly the curve. So what we found by recording the slopes of tangents at different points is exactly what the derivative curve is. You get the idea? All right. There's something else that we need to look at from when we see these two curves. I don't want to. Okay. What's up with the curves y equals f of x and y equals f prime of x? The black curve is y equals f prime of x. Its derivative. There are a few things that we need to observe and learn from this one. That is, look at when this y f prime of x graph has a 0 value, right? At this x value of some negative 1.2 or something like that. Would you agree that the derivative curve has a 0 value? Okay. What's the significance of the fact that the derivative is 0? Let me repeat that question. Please pay attention. What is the significance of the fact that the derivative function has a 0 y value? What is the derivative? Oh, it's the slope of the tangent. Okay, the slope of the tangent is now 0. So that means when you look at this curve y equals f of x, at this x value where the derivative is 0, if you were to draw a tangent, that's going to be horizontal. All right? Now you might wonder, yeah, so what's the big deal if the tangent is horizontal, man? Yeah, I agree. I'll come to it in just a second. Now, is the derivative function's y value 0 at any other point? Yep, somewhere here around 0.5 something. It is 0. What's the significance of that y value being 0? Again, the same thing. The tangent is horizontal at that point. Now, the significance of that is, notice what's happening where the tangent is horizontal. Up until now, here the tangent was, maybe I'll start to show the tangent. Okay. Here, as we started at the leftmost point, is the tangent positive? Does it have a positive slope? Yeah, it does. Why is it positive slope? If you look at the rise over run, the rise is positive, and for a positive run, right? When the run is positive, the horizontal, the rise is also positive. Maybe I should show this. Check this out. This positive 1 represents the run, and the corresponding rise is a positive 11.75. So certainly we can say that this tangent has a positive slope, right? So that means this curve has a positive slope at the leftmost point. Now I'm going to move this A, and is the slope still positive? Yep, the slope is still positive. That means the thing is curved sort of up like that. The curve itself is curved up. Now, as I keep moving here, where that A, that point which is drifting, where it occupies a 0 value, that is just about, oops, I went past. So somewhere, I cannot make it exactly 0. But right around there, this one has a 0 value. The tangent is horizontal. What else do you notice where the tangent is horizontal? That function has reached a maximum and then coming back down, right? It was increasing, and then where the tangent became horizontal, that's where it started to change. So that's why we are interested in where the tangent is horizontal, where the derivative is 0. Okay, we'll talk about this application of this in other places, but just wanted to give you a heads up on it. And also, notice here, once again, the tangent became horizontal, but what's the significance here? Well, we don't have a maximum here. Instead, the function, the red one, has a minimum value at this point. So a horizontal tangent is the place where the function will attain a maximum or a minimum value. There would be some exceptions, but in general, that is the case. Okay, we'll talk about all the exceptions and everything toward the end of the semester. Fine. Anything else that I need to point out? Okay, so we have derivative as a function. This is what I wanted to talk about first. Cool? All right. Is there anything I need to... well, that's the graph I just have. Okay. Now we need to get into this concept called differentiability. This is a very interesting and important concept, especially for mathematicians. Boy, is a function differentiable? That's a question they keep asking quite a bit. So let's see. What's the definition of it? A function f is differentiable at a point A if f prime of A exists. What is f prime of a? That limit thing. Limit as h approaches 0 of f of a plus h minus f of a over h. If that f prime of a, that limit exists, then the function is differentiable at the point. Otherwise, if that limit does not exist, then the function is not differentiable at that point. Cool? Are we good about the differentiability point? Can you figure out f prime of a or not? Would that turn out to be a nice value or not? If it is, good. Then the function is differentiable at that point. And also, once we talk about differentiability at a point, then we can talk about differentiability on an interval. What is an interval? A whole bunch of points, right? When I say the interval 1 to 2, what I mean is every real number between 1 and 2. 1, 1.01, 1.1, 1.01, 1.001, all kinds of numbers between 1 and 2. So, if this function happens to be differentiable on an open interval AB, then it is differentiable at every x in that interval AB. When can we say that a function is differentiable on an interval, on an open interval especially, say AB? If it is differentiable at every point in that interval. As simple as that. Okay? Now, a function f fails to be differentiable at x equals a. There are some cases where the function will not be differentiable, and that is going to be my next focus, and I really want you to pay attention to this. Okay? When is a function not differentiable? And for that, I'm going back to Geogebra. Non-differentiable 1. This is my first case. So, take a look at what I have. I have a graph of a function that looks like this. Maybe I'll increase the thickness of this.